Now that we've learned about temperature, we're going to talk about heat and heat transfer. So, heat is related to temperature, but temperature and heat are not interchangeable. So, heat is the spontaneous transfer of energy due to differences in temperature. So you need a temperature differential to have heat, but heat and temperature are not exactly the same thing. And so you can see that with the units for heat. So because it's energy, you can talk about heat in units of joules. Then there are other units that we use sometimes, like the calorie. So this is the energy needed to change the temperature of 1 gram of water by 1 degree Celsius or 1 Kelvin, because remember, a change in temperature of 1 Celsius is the same as a change in temperature of 1 Kelvin. The kilocalorie, or the capital, so this is lowercase c calorie. If we write calorie with a capital C, that is a kilocalorie, or 1,000 calories. And this is typically what's shown on a packaging for food, is this capital C calorie. And this is the amount of energy needed to change the temperature of water by 1, or change the temperature of 1 kilogram of water by 1 degree Celsius or 1 Kelvin. And then the transfer between calories and joules is that 1 capital C, or kilocalorie, is equal to 4,186 joules. So now that we understand heat, let's talk about heat transfer. So heat was the transfer of energy between two things that have a different temperature. So how does the physics of that energy transfer actually happen? So this equation is what will govern heat transfer. So heat transfer is this capital letter Q, and it's equal to the mass times the specific heat times the change in temperature. So the specific heat is this is inherent to a type of material. So if you have, for example, copper will have a specific heat of 387 joules per kilogram per Kelvin. And something like water will have 4,186 joules per kilogram per Kelvin. So different materials will have their own different specific heats. And so let's do an example problem where we apply this equation. So the example that we're going to work is we're going to calculate what heat is needed for a copper pot filled with 2 liters of water to be brought up to the boiling point from 15 degrees Celsius. So you want to cook some pasta, you need to boil your water, and we're going to talk about the heat that's needed in order to do that. So first, let's start with writing some things down. So for the copper pot, the specific heat is going to be, and I'll do specific heat Cu for copper, 387 joules per kilogram per Kelvin. Oh, and let's say this is a 5 kilogram copper pot. And then for water, the specific heat is 4186 joules per kilogram per Kelvin. The boiling point for water, so the final temperature that we want to get to, is 100 degrees Celsius, and our initial temperature is 15 degrees Celsius. So our delta T, final minus initial, is 100 minus 15. And so our delta T is 85 Celsius. And then because the scale of Celsius and Kelvin is the same, that's the same as a change in temperature of 85 Kelvin. Then the last unit that we'll have to think about is the amount of water. So that's 2 liters of water. And if we remember when we were talking about fluids and volumes, 2 liters of water is actually 2 kilograms of water. Okay, so now we have, if we think back to our equation, Q equals M C delta T. We are basically going to use this equation once for the copper pot, and we'll do it once for the water. And then once we have those specific heats, to get the total heat that we need to input into the system, we'll add the amount of heat we have to put into the pot plus the amount of heat that we have to put into the water in order to get it up to the boiling point. Okay, so let's start with the copper pot. So we have M, specific heat copper, delta T for copper. So the mass of the copper pot was 5 kilograms. The specific heat for copper was 387. And the delta T, we'll assume that the water in the copper pot started and ended at the same temperature. And so this would be 85. So the heat transfer for the copper pot Q will be 164,475 joules. And then we'll repeat the process for the water inside the pot. MCH2O delta T. So the mass of the water was 2 kilograms. The specific heat for water is 4186, and the change in temperature was 85. So when you plug that into your calculator, you get a specific heat of 711,620 joules. And the total, we just add those two values together. So pot and water. So 164,475 plus 711,620 gives you a total heat transfer 876,095 joules. And so another thing that you could calculate, how much heat did we have to put into the pot versus how much we put into the water. So to figure that percentage out, we'll just take the heat that we put into the pot divided by the total, multiply by 100 to get it as a percentage. So 164,475 over 876,095 times 100%. And that gives you 18.77%. And then you could just subtract 100 minus that 18.77 to get the percent that went into the water, or we can calculate it in the same way. So the heat that went into the water divided by the heat that went into the pot, or the total heat we needed to add to the system, times 100%, and you get 81.23%. And so this pot was fairly efficient at being a vessel to heat your water in. So only 20% went into heating up the pot, and 81% went into heating up the water. And you need some container to hold your liquid in, so this wasn't a bad choice for how we were going to boil our water to cook our pasta. Something interesting happens when you continue to add heat to a material after you've reached a certain temperature, or if you cool something, continue to take heat away from a system or a material after you reach a certain temperature, and that's what's known as a phase transition. So for this class, we'll mainly focus on the three phases of matter that are liquid, solid, and gas. And let's make a graph where we have temperature on the y-axis, and we have the change in heat on the x-axis. And let's just do this for water. And let's say we start with ice down here in the bottom left corner. We increase the temperature of that ice. And what happens if you make ice too warm? It'll start to melt. But when the ice starts to melt, even though I'm putting more heat into the system, my temperature doesn't actually increase until all of my ice has melted. So in this plateau region, we're a mixture of ice and water. Then once all of my ice has melted, if I keep putting more heat into the system, now my temperature will start to rise again. Now I'm all water. And this transition point where we start to get the ice to melt into water for normal atmosphere pressure will be 32 degrees Celsius or oh, will be 32 degrees Fahrenheit or 0 degrees Celsius. And so that would be 32 degrees Fahrenheit here, 0 Celsius here. And then if we keep increasing the temperature of water enough to 100 degrees Celsius or 212 degrees Fahrenheit, now the liquid water will start to evaporate. And so now we have water and steam. And then eventually, once you've evaporated all of your water, you can keep heating your steam up by increasing or you can increase the temperature of your steam by continuing to add more heat into the system. So these plateau regions in the graph are the regions for your phase transitions. And as you should notice, once my phase transition starts, I keep putting heat into the system, but I don't increase the temperature. And so the heat transfer that goes into these phase transitions will have an equation that looks a little different from the heat transfer equation that we saw previously. And there will be a heat transfer equation for each different transition state. So M is always the mass. The Q is always the heat transfer. And this L is called the latent heat. LF is the latent heat of freezing. LV is the latent heat of vaporization. And then we can't see it on this graph, but if you start playing with the pressure of your system, you can actually get the transition from solid straight into gas, and that's called sublimation, and this is the latent heat of sublimation. And so these latent heats are, again, just going to be specific to the type of material. So just like there was a specific heat for copper and water, there would be a latent heat of freezing, latent heat of vaporization, and latent heat of sublimation for any different element or compound that you can think of. So if we want to see how latent heat works, let's say we think back to our previous problem, and let's say you're boiling your water to make pasta, but you completely forget about uh, the boiling pot and go do something else. And when you come back, all of the water has evaporated. So the heat, the specific, or the heat that goes into vaporizing all of that water, there were 2 kilograms of water in the pot, and the heat of vaporization, the latent heat of vaporization for water is 2,256 times 10 to the third, and that would give you a total heat that it would take to vaporize all of that water as 45,112,000 joules. Now that we've learned about heat transfer and latent heat, we're going to learn about methods of heat transfer. So there are 3 methods that we'll talk about for this class: conduction, convection, and radiation. Conduction, there has to be physical contact between the two objects with different temperatures. Convection, there is contact through some intermediate medium like air or a liquid. And then radiation, there's no contact required. Photons will carry the energy. And so radiation is how we get energy or heat from the sun, even though there's the vacuum of space between us and the sun. So we'll look at a heat transfer equation for each of these heat transfer methods. For conduction, and we'll look at the heat transfer per unit time for each of these. So for conduction, this K is the conductivity. So that's just a measure of how easily something can conduct heat, and that will be an intrinsic property of that material. So for example, a metal will be very good at conducting heat, and something like rubber would be a poor conductor of heat. Capital A is the surface area. These two T's are just the temperature, so this is change in temperature, or the difference in temperature between the two objects. And then D is the distance. And that would be the distance the heat has to travel between the hot and the cold side of the object. Then we'll have one of these for convection. And again, the lowercase t is just per unit time. And the convection equation will look just like the heat transfer equation we've already seen. And then for radiation, the heat transfer per unit time will look like this. So this sigma is the Stefan-Boltzmann factor, which is just a constant. This is again the surface area. And this is T to the fourth. This is temperature to the fourth. And the Stefan-Boltzmann factor is 5.67 times 10 to the minus 8. And the units on that are watts per meter squared per temperature to the fourth. And so these heat transfer rates are what these equations are really representing. So heat transfer has units of joules. We're dividing by time. So that's really a power. And so these are all the power that would be radiated or convected or conducted. And so the units for all of these would be watts.